Good morning, guys. So the first thing that I want to ask you this morning is, can you hear me well? Can you please type or just unmute your phone, your microphone, and let me know that you are good, that you are listening well this morning?
Yep, I can hear you good.
It's good.
Loud and clear.
Okay, perfect, perfect. Thank you so much for letting me know. So while we are doing this presentation, we are going to be having people joining in. So the first thing, as I promised, that I want to do with you this morning is that the last time we met, and that was Thursday, I was having some issues with Multisim. So I was able to fix the issues, and now everything is working the way it should work. So I can give you like a quick demonstration on how the capacitor works on a rectification circuit. So right after we see the demonstration, then we are going to do the Zener diode, and that's what we are going to cover. I'm going to cover about 7 slides about the Zener diode, and also I'm going to give you another demonstration on Multisim on how the Zener diode works. Okay, and then that's going to be the end of the class, and then I'm going to be open for any questions that you might have, even when you can ask questions at any point in time. So let's begin here first. Okay, so let's begin with Multisim. What you see here is a full bridge rectifier. Again, the same thing. We had a power source, and then we have a step-down transformer. Already on this probe, you can see that we have 28 volts, and that's the RMS voltage. And we have a peak-to-peak voltage, which is equal to 79.2. But what really matters is that this is a simulation of the same lab that you are going to be doing once you return to the college. So in this instance, we have 28 volts, which is the input voltage to the bridge rectifier. And in this instance, I have a 60-watt light bulb. On the first part of this project, you are going to have the 60-watt light bulb, a 25-watt light bulb connected with your bridge rectifier. So let me show you that from your booklet. Give me 1 second while I open this booklet. Okay, so here, back to the so I'm going to share the booklet with you. So this is something that I show you. Can you see that? Can you see the booklet?
Yep.
Okay, perfect. So something that you are going to see first is that I already showed you this, the 28 volts with the bridge rectifier and your light bulb. The light bulb is going to be switching between, and we are going to simulate the same thing here. We are going to be switching between 25 watts, 60 watts, and 100 watts. And then, because this is a simulation, I'm going to be able to add a 660 watt light bulb in that case. We don't have it in the college, but in this instance, instead of a heater, we are going to use the same light bulb to simulate that we are putting 660 watts. The reason why we are going to have different loads is because I want you to be able to see what happens to the ripple voltage. The actual rectified voltage is going to change with the capacitor. And also you are going to be able to see that because we have a 500 microfarad capacitor. But I want you to be able to see that once we have different loads connected to that capacitor, how the ripple voltage is going to increase. That's what I want you to be able to see, okay? And also how the mean voltage will be affected as we apply different type of loads. So back to the simulation then. Any questions about that? No questions? I guess that I'm gonna assume that the silence means that you don't have any questions at this point. Okay, so if you happen to miss me at any point in time, please let me know. Because I just got a message on my computer that say that my internet wasn't stable, but everything seems to be okay, you know, on my end. Excuse me 1 second. I am on a meeting, Jochi. You gotta go upstairs.
He wants to learn, Garcia. Come on.
Yeah. Okay, sorry about that. Okay, so let's continue. Let's keep going. Sorry about that, guys. So can you still see the multisim?
Yep.
Okay, perfect. So let's do it. So let's begin right here. Okay, so this is the same oscilloscope that Tektronix that we have in the shop. The only difference with this one is that this one has 4 channels. We have the same type, but I mean the one that you are using have only 2 channels. Today we only need to use 1 channel anyways. So let's begin. And also I'm going to cycle you through the different functions of the oscilloscope. So let's begin right there. Right at this point, okay, so you can see on the oscilloscope that we have, okay, so we can see the rectified signal. So we have a full wave rectification. And at this point in time, let's do the following. I'm going to use, instead of plugging in a voltmeter right at the load, what I decided to do is that I decided just to measure the voltage using the oscilloscope itself. So I am going to use this function here, which is called measure. And on measure, you can see right here at the bottom, how much is the rectified voltage is 23.6. It fluctuates slightly. And also you can see how much is the ripple voltage, which is 12 volts. So I know that we have done this in the past, but I want you please to do the following. I want you to use your calculator and check to see how close we are, you know, from a calculation standpoint to the actual measured voltage that I have on my oscilloscope. So I'll give you a few seconds while you do that calculation. Are you okay? Done? Everyone seems so quiet that it's kind of scary when everyone is so quiet. So, okay, so have you done so far the 28 volts times 0.9? That's giving you how many volts? So anyone can interject and share.
71.1 volts.
Oh, 28. It's not 79. It's 28 volts. That's the peak to peak.
25.2.
Which is the applied voltage times 0.9.
25.2, yeah.
Perfect. So do you know why a small discrepancy between my measured voltage here and your calculated voltage? It's because of the actual diodes, okay? It's because of the rating of the diodes that I'm using for the simulation. That's why we have a small discrepancy. But it's a pretty close value. Also, with the ripple voltage, when you did the 28 times, how much it is? 0.45?
0.43.
0.43. Okay, so how much did you get for the ripple voltage?
Around 12.
Around 12, which is this RMS voltage that we can see that we are measuring at this point in time. Okay, so it's very, very, very close, that one. Okay, now, that being said, let's see what's going to happen. Okay, so I want to show you first that here on this light bulb, so I'm going to stop the simulation. I want to show you that the values, can you see the values here? I decided to go with a 60-volt light bulb because I want to see the animation. I want to see the light bulb turning on and off. It's just because of that. If I use a 120-volt light bulb, it would be the same thing. So in this instance, we are using a 25-watt light bulb. Okay, so the simulation is going to be based first on 25 watts. Now I am going to plug in the capacitor, and let's see what happens when the capacitor is plugged in. Look at that. I want you to be able to observe what has happened at this point in time. So now you can see that our pretty much like our voltage, everything has changed. So let's begin here. You can see first that the shape of the signal has changed, right? And that is because the capacitor is charging and discharging over the load. Now, I want you please to pay attention also to the values. The mean value, in this case, went up to 36.1 volts. And the RMS value was reduced to 1.07 volts. And that's very interesting because by connecting the capacitor in parallel with your load, we were able to filter most of the ripple voltage, as you can see in here. And that's why we are using the capacitor as a filter. And we accomplish what is called filtration. Any questions about that?
Nope.
Okay, perfect. So it makes sense so far. So let's keep going. I want you to be able to see as well the following. Let's see if the simulation is going to work properly. If I remove the light bulb. Look at that. So you can see that when I remove my load, that we have a perfect flat DC signal. So in this instance, I mean, like if you want to calculate, actually, like I want you to do the following, please, pretty quickly. How much it would be the peak voltage of my input RMS? Remember how to calculate the peak voltage of the RMS?
Yeah, divide by 0.707.
Perfect. So you are going to be dividing by 0.707, and that's going to give you 39.6 volts, right? That's what you get?
Yeah, that's what I got.
39.
Perfect. So you can see in here that the actual rectified voltage is 38.8, which is very, very, very close to the actual peak voltage or max voltage of the input signal. The reason why that's happening is because, of course, we have a small voltage drop on the diodes. Remember, the diodes use roughly about 0.7 volts. And that voltage drop is going to be the factor that causes this DC voltage without any load to be 38.9 instead of 39.6. It's because of that small 0.7 volts drop, as you can see in there. Now, as soon as we plug in our load, then we can see right away the ripple voltage developing. Why? Because in this instance, the capacitor doesn't have enough capacitance in order to keep our voltage all the way up to 38.6, right? because we don't have a capacitance which is large enough. That's why we are going to be able to see that we have this a small ripple voltage. I mean, if we were able to increase the capacitance, then we would be able to reduce the ripple voltage and obtain again pretty much a perfect DC signal. Now, let's keep going and let's plug in now different loads. So let's go from 25 to 60 watts and let's see what happens. When we go from 25 to 60 watts, please observe these two values here between the mean voltage and the ripple voltage, and let's see what happens. Can you see what happened right away? Okay, so you can see that the signal has changed because now we have a greater ripple voltage, but also the mean voltage was reduced because the capacitor is discharging at a faster rate with the bigger load. Any questions about that?
Nope.
Makes sense.
Makes sense so far? So let's go to the next load. The next load that we have in the shop, it would be 100 watts light bulb. So in that instance, let's see what's going to happen. Look at that. So now the ripple voltage have increased a little bit more and the mean voltage have been reduced a little bit more. So we can see a consistency that as the ripple voltage is increased, we are going to be losing our mean voltage, okay? And it's because the capacitor, it is actually discharging at a faster rate. Now let's go to the last example, 660 watts load. Look at that. So I want you to be able to notice, okay, this line, which is the horizontal line. Okay, you can see that that is pretty much the horizontal line. On the horizontal line, this signal is indicating 0 volts. And I'm only doing this, I'm only going to the ground reference just to show you that the reference point is going to be where we have the yellow line. It's going to be the horizontal line. So now when we go back to our DC voltage, let's get back to measure, you can see that our ripple voltage have increased dramatically and that our mean voltage has been reduced dramatically as well, because now the capacitor is discharging at a faster rate. If we were to increase the capacitance, we would be able again to reduce the ripple voltage. And that's pretty much what you are going to be learning when you do the lab. One last equation that I got to throw there. You would be able to see in here that like if I wanted to calculate this value, my ripple voltage, I mean, I cannot go with the 0.43 anymore because the 0.43 is going to work when I don't have the capacitor in the circuit. So if I wanted to calculate my ripple voltage, I have to use a different formula that I am going to put on the screen. So the formula that we are going to use for that will be, okay, I'll show you here. We are going to say in this case that E ripple is going to be equal to the E max minus the E minimum divided by 2 and then multiply by 0.707. Now, you may wonder, okay, so how do I get my max and minimum from the oscilloscope? So let's get back to that. If any of you is having any issues with following, please let me know, okay?
No, it's good so far.
Good so far, perfect. I'm glad to hear that. So let's go back to the same example. I want you please to observe on the oscilloscope that there's another function right underneath measure that is called cursor. When I click on that function, you see that couple dashed lines appear. So what I'm going to do, I have here cursor 1 and 2. So I'm going to move them accordingly. I'm going to be moving number 2. I'm moving this to the bottom. I'm going to move this to the bottom of the signal that is being displayed on the oscilloscope. Okay, right there at the bottom. And this one is going to be touching the top. Okay, here. Okay, so we can see that the maximum voltage as per cursor 1 is equal to 37 volts. Okay, and the minimum voltage so far, you know, from the horizontal line point of view is equal to 26.9. Excuse me, is equal to 10.1 volts. Okay. So now, when we calculate the difference in voltage, the difference is equal to 26.9. So now, if we take the 26.9 volts, which is the difference between the 37 and the 10.1, and we divide it by 2, and then we multiply that by 0.707, we actually get how many volts? Did I go too fast?
No, you're good.
Okay, so how much do you get, guys?
9.51.
Perfect. And what is the, okay, so I went back from cursor. I'm going back to measure, and we can see that the ripple voltage is equal to 9.27. Okay, it changes slightly, so it's rather close. The calculation to the measure value with the oscilloscope. And that's the formula that we would use. Okay, so that's going to be the formula that we are going to use when we want to determine our ripple voltage. So the other formula, which is the 0.43, that's going to work only when we have, I mean, when we have a full wave rectified voltage without the capacitor. Once we insert the capacitor and we change the load, then we are going to be getting different ripple voltages. And that's something important to keep in mind. Okay, any questions about that, or we are good now?
So the one that you just showed us, the Emax, Emin, that's, you use that when you're doing capacitors.
Perfect, perfect.
Okay.
So you're going to be using that when you are doing capacitors, sir. Absolutely.
And is that one only for full bridge rectification, or can it be used for half?
No, that's going to work. That works for everything.
Okay, sweet.
Yeah, because it's going to be based on max and minimum voltage. Anyways, if you don't have any questions about this simulation, then let's move on into the other topic.